Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. In the previous lecture, we have seen some sort of a sketch of the so-called proof of singular value decomposition. We've shown you some of the properties of this singular value decomposition, the fact that you can actually obtain orthonormal basis for not just the image but also the kernel of a given matrix, and the beautiful fact that this is independent of whether the matrix is square or rectangular, fat or tall, right? The singular value decomposition always exists and it always gives you this orthonormal basis, right? So today we shall start off this lecture by seeing a couple of more consequences of this singular value decomposition and how it beautifully has an interplay with the notion of what a matrix does to a vector. Okay, so if you recall, to start with, or rather to refresh our memory, we had this matrix A which can be written. So let's say this A is an M cross N matrix. It can be written in this following manner as let's say maybe I call it the square root of sigma hat, perhaps, yeah, and then the 0 0 0 and V Hermitian, right. So where of course this came from the space of M cross M complex matrices, the V belongs to the space of N cross N complex matrices, right, and this obviously has a size of N columns and M rows. So this is M cross N, where of course this part, so this is just a recap of what we have seen yesterday, this part is a diagonal matrix containing only positive entries in its diagonals, those positive entries being precisely the singular values of the matrix, right. Now if you think about it a bit, there's another way in which we can write this, yeah. So let's say we write this as u1, u2, so on and so forth till right. So this is my U matrix where each of these ui's are basically column vectors, m tuples of complex numbers, right. And then I have this sigma 1, sigma 2 till sigma r, remember, where not just the fact that these sigma 1 through sigma r are positive numbers, but also the fact that there is an ordering, yeah, till we have sigma r. And the way we have ordered this is that of course this r is at least equal to 1, yeah. So the way we have said it is that this, at least this first r fellows are non-zero. If they are all 0, then of course it is a 0 matrix, it does not make any sense that way. Alright, and in addition to that, we then have this V1 Hermitian, V2 Hermitian, so on till Vn Hermitian, where recall that V1 or rather Vi is a complex n tuple, right. Now once we have this, written down like so, what can we then do? Well, we can then say that this A is further equal to, notice very carefully, whether I first operate these two first and then subsequently multiply with this, or I operate these two first and then subsequently multiply with this, the conclusion is going to be, it is sigma 1 times u1 v1 Hermitian plus sigma 2 times u2 v2 Hermitian plus so on and so forth till sigma r times ur vr Hermitian. That is it. What we observe in addition to this is the fact that each of these individual terms are simply nothing but rank 1 matrices. I urge you to check that. Remember, this is a column vector, and this, because you have taken the Hermitian operation, becomes a row vector. So, a column vector times a row vector, yeah, it is always going to be a matrix. Not just that, you will see that every row is a scaled version of the other row, scaling factor being the corresponding entries of the U matrix. By the same token, you can also think of it as every column being a scaled version of the column U1, yeah, scaling factor being the entries of V1, right. So, therefore, it has only rank 1 because there is only one linearly independent column and one linearly independent row, right, respectively, that span the column span or the row span respectively, right. So, essentially what we are saying is that it is a beautiful way of seeing that any rank R matrix, remember that if you have R non-zero singular values, then the rank of this matrix is R. Yeah, we have already shown you that in the previous lecture. We have proved this, right, that ultimately what you end up with is that if you have this singular value decomposition with R non-zero singular values, yeah, then the rank of the matrix is R, because the image of that matrix has a dimension equal to R. We have taken some pains to sort of prove that in the previous lecture, but eventually we did get there. So, that being the case, we can say now this, loosely speaking, that any rank R matrix can be written as a sum of R rank 1 matrices, and clearly the singular value decomposition provides you a very elegant way of doing that. Is that the only reason why we are interested in this? Well, of course not. Now, think of this. Suppose I choose V in Cn, which is basically the domain of the matrix A, right. Therefore, V can be written as summation, let us say some Ci Vi, I ranging from 1 through n, right. It is an n dimensional vector space, so you need n elements in the basis, and we precisely choose the columns of the V matrix, not the V star, but the V matrix, the columns of the V matrix, which are essentially the transpose conjugates of each of these individual rows here that you see, right. So, those as the basis. All right. Once we have done that, if we want to observe the effect of A on this particular V, yeah, what we might then notice, of course, this is nothing new, we have already seen this. This is nothing but, you see, summation sigma I ui vi Hermitian, I ranging from 1 through R, that is what A is, right. So, this is basically what A is, times V. So, then I get to write this as I is equal to 1 through R sigma I ui vi, and then there is a second sum here. There is a second sum here which is summation Ci Vi I going from 1 through n. But now observe that this, again by the same token, the same manner in which we have written this down earlier, if you now open up these brackets and appear to be a little inelegant. So, you have sigma 1 u1 v1 Hermitian times c1 v1 plus c2 v2 plus dot 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 till cn vn plus sigma 2 u2 v2 Hermitian times c1 v1 plus c2 v2 plus dot 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 till cn vn plus dot dot dot, and finally you arrive at the last term, that is sigma r ur vr Hermitian times c1 v1 plus C2 V2 plus maybe there is seated somewhere as a CR VR. Why I am writing this specially will be clear in a bit. Okay, that is what this is. But now notice that in the midst of all this product operation that we are carrying out, yeah, when I take V1 Hermitian operated with V1, then I get unity, because this is an orthonormal basis. The columns of V matrix are an orthonormal basis for Cn. What about this operation? It leads to 0, right? V1 Hermitian V2. Similarly, with every other fellow, this leads to 0. The only non-zero element arises when I have this operation. For the second fellow here, this leads to 0, this leads to 0, and everything else leads to 0 except for when I operate with this. I just filter out C2. So this term here filters out C1, this term here filters out C2, similarly this term here filters out CR, correct? And therefore, what I get as a consequence is C1 sigma 1 U1 plus C2 sigma 2 U2 plus dot 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 till CR sigma R UR. In other words, all these n tuples, the C1 through Cn, out of them only the first R are retained, alright. Apart from that, we also notice that each of these is amplified by precisely the singular value, and of course in the image for which U1 through UR is a basis, yeah, you get the coefficient of this. So when A acts, the matrix A acts on a vector V, where V belongs to C n, right, this comes from C to the n, yeah, what does it do? It maps it to a point in the image. Image is what? The span of U1 through UR, yeah, that is the image of A, as we have seen the other day, right. Not just that, but the fact that we now also know exactly in what direction, what is the gain, yeah. So if the vector V had a component C1 along V1, then its component along U1 will be C1 times sigma 1. If the vector V had a component CK along VK, then its component along UK in the output in the image would be CK times sigma K. In other words, sigma K is precisely the amplifying factor along the direction UK for an input along the direction VK. If I am to think of this matrix as an input output sort of a map, right, then these inputs could come along different directions. They could come along V1, V2 dot 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 till Vn, as we have seen, right. We can think of them as inputs like this, and the outputs can come along U1, U2 dot 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 till Um. It so happens that there is this beautiful coupling now. The moment I say that there is this component, say, let me use a different color. So this is, let us say, a component alpha 1 along V1, then correspondingly the output, in the output I will see that this is reflected as a component alpha 1 times sigma 1 times the component along U1. So any component alpha 1 along the input direction V1 reflects as an output along the output direction U1 scaled by a factor sigma 1, yeah, and this is beautiful. This is what orthonormality or orthogonality brings with it, right. That is the beauty of singular value. Of course, you can think of this singular values as generalized case, in which case you can even go beyond sigma r by saying that sigma r plus 1 is the r plus 1th singular value, which is essentially equal to 0. So then you see that any vector, any input that you apply along the r plus 1th direction through till the nth direction, it gets reflected as a 0 multiplication, right. So there is no amplification whatsoever, there is a 0 amplification, so it is completely suppressed. So that is basically saying that those belong to the kernel of this linear map. So if you give any input along the kernel direction of the, in the kernel, within the kernel of the linear map, then the output is pulverized, there is no output, it spits out nothing, right. So, that is essentially what this singular value decomposition does. And the moment we have this at our disposal, there is this very useful definition that we often come across in matrix theory and in general in case of operators as well, or transformations. So, we say that, you see now, the sigma 1 of A has a very special role to play. It is saying that, okay, this is basically the maximum amplification such that over all V you can choose from C to the n and V is not equal to 0, such that you take the norm of AV and divide it by the norm of V. In other words, what is this? What this is saying is that, well, if you give an input, by what factor is it amplified? Okay. So, now you think of this here. What is after all the norm of V? If you look at the norm of V, it is nothing but the square root of C1 V1 star plus dot 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 plus Cn Vn star times C1 V1 plus dot 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 Cn Vn. But now these are orthonormal sets, right, this set of V1 through Vn. So, therefore, this leads to nothing but C1 squared plus C2 squared plus dot 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 till Cn squared, alright. So, this is what the norm of V would be, any vector. And now we are saying that what is the norm of AV? After all, we also know what AV is going to be. AV is going to have nothing but only the first R components. So, AV is going to be basically C1. Look at what AV look like. It had only R components. So, again U1 through UR is an orthonormal set. So, this is C1 squared sigma 1 squared plus dot 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 till CR squared sigma R squared. So, essentially this then boils down to, So, essentially this then boils down to the max over C1 squared plus C2 squared plus dot 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 Cn squared not equal to 0. So, it is not the 0 vector after all, that is the only assumption we have made when we have said that this V, it is not, it is a non-zero vector. And what we are saying is then we are trying to maximize this particular ratio C1 squared sigma 1 squared plus dot 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 till CR squared sigma R squared upon C1 squared plus C2 squared plus dot 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 till Cn squared. Now, notice, so now you notice that if you want to really maximize this quantity, if you really want to maximize this quantity, what should you do? What should your choice of C1, what can you play around with? The choices of C1 through Cn. That is going to give you the vector that you are choosing, because the moment you fix up C1 through Cn, you have essentially fixed up this vector in the input space, this vector in Cn V, which maximizes the amplification factor, the gain, alright. But now this is what the expression is going to be. What is this after all? What can we say about this? Now, suppose you say you normalize this. So, now this can also be thought of as, because I am saying that this can be normalized, I can just say that this is tantamount to, without loss of generality, Cn squared is equal to unity. That is what this is, and then you can get rid of the denominator, and this is just the maximum of C1 squared sigma 1 squared plus dot 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 till CR squared sigma R squared. And do not forget that now there is an ordering between this sigma 1 through sigma R, with sigma 1 being the largest component, right. So, if you want to choose this, if you want to now choose this C1 through Cn, C1, C2, C3 so on till Cn, such that there sum of their squares is unity, and at the same time this function is maximized. What should you choose? shouldn't you then choose C1 to be 1 and the rest all to be 0? Yeah, it's like you have multiple portfolios, you have multiple investments, and clearly there is an ordering between them. One of them leads you the maximum profit, so you should then invest all your money in that particular commodity, right? And that is how you will reap the maximum benefits, right? Why should you invest your money in something that is known to fare worse than the best? So it's like you are allocating your resources being C1 through Cn, right? You are allocating your resources. So C1 goes with sigma 1, C2 goes with sigma 2, till Cr goes with sigma r. And we know that sigma 1 is the largest fellow, the one that brings me the maximum return. So then clearly this is going to be C1 squared sigma 1 squared with C1 is equal to 1 and C2 is equal to C3 is equal to dot 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 Cn is equal to 0. You are basically choosing the unit vector now, right? Which unit vector maximizes this, and you see that you should go with that which maximizes your return. If you for instance choose C1 to be half and C2 to be half, or rather that is going to be just what? 1/4 plus 1/4 half. So if you for example if you equitably distribute, C1 is equal to half, C2 is equal to half, C3 is equal to half and C4 is equal to half, yeah, and you know that sigma 1 is the largest. So only half of your investment, or rather 1/4 of your investment is being maximized. The remaining 3/4 is yielding you less than the maximum you could have got. So it makes then sense to go with that which is the most profitable. So the most profitable is the sigma 1, therefore this is nothing but sigma 1, right. So indeed the largest singular value also tells you the direction of the largest amplification and the gain. So along which input direction you would get the maximum amplification at the output, yeah. So if you have an input along V1, it gets amplified by sigma 1, which is the largest amplification for any vector along any direction. Similarly, among non-zero amplifications, if you do not consider a vector in its kernel, yeah, in the kernel of A, so among non-zero directions it is sigma r which gives you the minimum amplification, right. So because of this ordering, so that is also another thing that this singular value does. Of course, there are several other important and interesting properties of matrix theory that can be proved using this singular value decomposition, but this is per se not a course on matrix theory. So at this point we will stop our discussion on singular value decomposition and we will move on to something else which is also a very important topic for this course on robust control. As and when we will need this singular value and its singular value decomposition and its properties, which we shall quite often be required to use, in fact, we will call upon these properties and maybe build on them somewhat. But for the time being, this much introduction to singular value decomposition I feel should suffice for our purpose. So let me draw a line below that, and now we move over to the next important object that we are going to study, which is LMIs, linear matrix inequalities, yeah, very fondly often referred to as LMIs. Okay, so what is a linear matrix inequality? Now suppose we have a vector space, yeah, say X, okay, curly X, whatever we call it, right. Suppose we have this vector space, right, and we have a linear map F from this vector space to the space of Hermitian matrices, okay, such that this fellow, such that for any x belonging to this vector space curly X, yeah, Fx belongs to the space of Hermitian matrices, yeah, straightforward so far. And not just that, it's, remember, it's also linear. So we know what a linear map is. We have spoken at quite some length about what linear maps are, right. We know that they basically satisfy the properties of homogeneity and superposition, right. So, if you have a linear map that acts on one particular fellow and another fellow to yield two different points or two different objects on the image, right, then if you scale them, the two objects in the domain of the linear map suitably, then the corresponding elements in the image space are also scaled by the same factor, and then if you add them, then you can actually scale them individually in the image space and add them also, right. So, whether you scale them up and add them in the domain, or you scale them up and add them in the codomain, the corresponding mapped entities, that is, it really does not matter. That is the beauty of linearity, right. So, then we say that a typical linear matrix inequality would look like this. Suppose further we have Q which also belongs to H of n, right. Then f x less than Q for x belonging to this vector space X. Let me also box that in a different color, yeah, because this is exactly what an LMI looks like, is a linear matrix inequality. And let me draw your attention to the fact that when we talk about this inequality or use this inequality sign, in case of matrices, we have already defined or described to you what this inequality entails. Remember that we had this description of positive definite matrices and negative definite matrices and so on and so forth. So, it essentially means, this inequality that I have boxed in red now, it essentially means that fx minus q, remember fx is a Hermitian matrix, q is a Hermitian matrix, difference of two Hermitian matrices is also going to be a Hermitian matrix, because the space of Hermitian matrices is a vector space, right. So, what this inequality essentially means is that fx minus q would be a negative definite matrix, yeah. The most of these LMIs would be concerned with the problem of whether we can find an x such that this fx minus q is indeed negative definite, right. That is the feasibility question that we shall be concerned with respect to LMIs, and that is the first question we shall be concerned with. The second question, of course, being that if this is indeed a feasible problem, then go ahead and find a solution to it, right. And this will in turn involve a lot of interesting properties. We will see that these are very closely tied to the ideas of optimization, which we shall be using again very often in this course. In fact, this course is built on that, those premises. So, when we go into optimization, there are several other ideas like convexity and all, which we shall again get to very shortly, probably in this lecture. But first things first, so we have now defined what an LMI is, right. So, the moment we have defined this LMI, we are now in a position to give you some examples and also to get into a further detailed description of an LMI. So, now suppose, so this is where maybe we draw a line below it. We have actually described to you what an LMI is. Of course, these are all not very formal definitions per se, right. I am just, the idea of this course is to give you a very lucid grasp over the ideas rather than get caught up in memorizing definitions, okay. As and when we encounter certain technical terms which have very specific definitions, we might have to use some notations to describe them, but I will try to keep the language as lucid and as easy to follow as possible, so that we do not get into this formalism of stating things in the theorem lemma structure. We will try to minimize the use of such structures, right. Okay. Now, consider a basis for this vector space X, say given by okay, say V1, V2, these are capital V's I am saying, I mean arbitrary, these are just objects, right, whatever, depending on the structure of this vector space X, yeah. You can actually call them, you can call this variable chi, it looks like the chi variable, but okay, curly x or chi, whatever you want to call it. Anyway, so suppose we have, okay, let us say m, let us say there are m elements in the basis, okay. then any element in this vector space can be represented as x is equal to summation xi vi, right. That is after all the very definition of a basis. So, of course, we are, the moment we are saying it has got a basis that is finite, we are essentially dealing with finite dimensional vector spaces, needless to say, right. Now, if F is indeed a linear map as we have described it here, that this F is a linear map, remember, a linear map, then when we take f of x, can we not write this as f of summation xi vi like so, I going from 1 through m. But now due to linearity, the very fundamental property of linearity, we can then write this as summation xi f of vi, I going from 1 through m. Now note, what are these objects f vi's like? F is a map from the vector space chi or curly x to the space of Hermitian matrices. Therefore, f of vi definitely belongs to the space of Hermitian matrices, that is the image of the map f, the linear map f, right. So, therefore, let us define f of vi as fi belonging to Hn. Then we can say that f of x is nothing but summation xi fi, right, where each individual fi is a Hermitian matrix, and therefore, this entire inequality, this LMI business that we have now formulated, turns out to be, sorry, fx less than q is actually equivalent to and one and the same as summation xi fi less than q. So, it is basically a a scaled sum of certain Hermitian matrices, that is what this is. So, basically every LMI can be reduced to something that looks like this, but that is not the only reason why LMIs are attractive to us. Quite often in controls, and most so in this course on robust control, we will encounter LMIs in different forms which may not exactly give this particular look, which may not look exactly like this, and yet they do turn out to be LMIs. So, let us give an example. So, let us give the first example. For instance, we have A belonging to C, what should I say, n cross n, A belongs to C n cross n, say X belongs to the space of symmetric matrices. So, really symmetric, Hermitian, I mean when I am saying it is real, there is no difference between a symmetric and a Hermitian matrix, alright. So, then suppose we describe this A Hermitian x A minus x less than q. This is a LMI. I urge you to check, take this as an exercise and check that this is indeed an LMI, where of course this is your f of x. So, all that you need to basically check is that f is indeed a linear map from the space of symmetric matrices to the space of Hermitian matrices. So, first you have to check that A Hermitian x A minus x is also a Hermitian matrix. Of course, x is a symmetric real matrix, so it is also Hermitian. That goes without saying. The only part you have to check is A Hermitian x A, which is again very trivial to check that it is going to be Hermitian. So, it is indeed a map from the space of symmetric matrices to the space of Hermitian matrices. Is it linear? Well, of course it is. Just go ahead and check. Take x1 and x2 as two symmetric matrices and check whether alpha x1 plus beta x2 f of that, f of alpha x1 plus beta x2, yeah, is also, you know, satisfies the same properties, right? Yeah, then you will know that this is indeed a linear map, right? That f of alpha x1 plus beta x2 is equal to alpha times fx1 plus beta times fx2. That's all that you need to check essentially. And yeah, so that's pretty much it, right? Once you have satisfied that this is, and of course you know that the space of symmetric matrices is a vector space. Real symmetric matrices is a vector space. So there's really nothing to check here. So this is an LMI. Okay, let's look at something that's a little more complicated looking than this. So we can also extend this A Hermitian X A plus by plus y Hermitian b plus t less than 0, where of course again as before we can choose this A to be n cross n, b to be say n cross m, yeah, and t to be of course t to be Hermitian n, yeah, and say x comes from symmetric matrices again, yeah, x comes from the space of symmetry, yeah, that's the sign I have used. Let me use this as n cross n. Yeah, I might sometimes drop this n cross n, don't hold it against me. So when sometimes I take this as s n cross n, sometimes I take this as s n. Maybe I should use n because for Hermitian I am just using a single n. So yeah, it's understood that this is the space of symmetric matrices. Okay, just to be consistent. But we can say we can still have this y. This can come from the space of any m cross n matrix. Is that consistent? Let's check n cross m, m cross n. Yeah, we are doing good. So this is it. So now this, I put it to you, is also an LMI. Now you might at first glance feel like, what is the vector space from which we are choosing inputs? How is this an LMI and how do I pose this as an LMI? Remember, for an LMI you need to satisfy those properties, right? Look at the definition here. You need to satisfy. So what indeed, the first question you will be encountered with when trying to justify this as an LMI is, what is this chi, this vector space, or chi or curly x that we have defined here? In this particular example, the second example, what is the domain of the f? When I know the domain of the f, only then I can define this as some domain and then take an object from this domain and then map it through some linear transformation or linear map and then call it an LMI. Yeah, I have to pose it in that form, right? But unless I have actually found out what this domain is going to be like, it doesn't really make sense to talk about this as an LMI. And here is what we will do. So the idea that I am trying to push through this discussion is that often objects may not on the face of it look like an LMI and it might look challenging, but then you can massage them in such a way that you can get it to this well known form, provided you can choose this vector space suitably and the mapping suitably. You can often see that objects that do not, or inequalities or stuff that does not necessarily look like an LMI, can be massaged in a way to make it or give it an appearance of an LMI, and then it indeed turns to an LMI. Okay, so let's particularly, because I know the solution here, let's define Z as this Cartesian product. It comes from this Cartesian product of the vector space Sn cross R m cross n. So now listen, earlier it was very straightforward. X was basically our input to the fx, right, and we just defined this whole object as fx and we got our way through. But now from this, what do you do with y, what is x, how do you describe this input space and all that? It's not very straightforward, right? So let us say that we define our object in the vector space like so, and what is our vector space? And so then this becomes our vector space. So again, this is a concept from linear algebra that products of vector spaces, Yeah. So if you take products of vector spaces, they also become vector spaces themselves. Yeah. Maybe I haven't described this in much detail, but then you should have an intuitive understanding of this, at least in terms of Euclidean spaces, right. So you take R2 for instance and take its Cartesian product with R. Yeah, and what you get essentially is something that's isomorphic or that looks similar to R3. Yeah, that's what it is, right. So you have those smaller vector spaces Sn and Rm cross n that constitute that sort of you get this Cartesian product, and then you get to build up this so called bigger, very loosely speaking, bigger vector space, which is this chi or curly x in our case, right. So I urge you to check as an exercise that this is a vector space. Yeah, once you've satisfied yourself that this is indeed a vector space, then really there's nothing much to do, because now you can just define the f of z. Yeah, you can just define this f of z in this fashion, right. You can just define this f of z in this fashion, where this f picks out any z like this and passes it through a map. So this f picks out this z that looks like this coming from this vector space chi and passes it through a map. Okay, maybe I should be a little more specific and clear about this. So when I say passes it through this map here, the map only consists of this part. Okay, so this is what I would call f of z, and then I finally get the form it is less than minus t. And notice that T is already a Hermitian matrix, therefore so is minus T, right. So therefore now we have all the requirements of the LMI in place, and now subject to the way we have defined this vector space chi, we indeed have an LMI on our hands, right. So that is a big lesson. Before we conclude this part, of course LMIs are something that we will not be able to get rid of, and we do not want to get rid of throughout this course, right. So for the time being we will put a stop to it and get to some other aspects. We will return to LMIs very shortly again, but before we do that I want to give another example of LMIs to sort of motivate further that, well, objects that often do not look like LMIs are indeed LMIs. So think of this: Ax plus b whole Hermitian times Ax plus b minus c star x excuse me minus d is less than 0. Okay. So what we are saying here is that, look, where this x comes from, say c n, it is a vector. Yeah, a comes from c n cross n, b also comes from c n, right, c also comes from c n, or yeah we can do that, and also d comes from c n, right. Now note that this, clearly you can see there is a quadratic form here. Yeah, Ax plus b is like a vector x plus something, right. The components of x1, x2, x3, they are, you take linear combinations of those components, that is what Ax does. Yeah, it is a linear map after all, right. So it maps from Cn to Cn, and then you take Ax plus b, so you translate it, you shift it a bit after taking the linear map, and then you take its sort of inner product with itself. So that is like a norm, therefore it is a quadratic function. Clearly you will have x1's, the norm of x1, norm of x2, things like that, terms like that are quadratic in the components of x. Okay. Maybe I can choose this x to come from Rn rather than Cn, but anyway, yeah, okay, let me make this Rn. Yeah. Yeah, fine. Okay. Maybe make the C also Rn then, and then the C star doesn't really make much sense. No, let me retain it as it is. Let's not simplify things. That becomes too simplistic. Anyway, right. So now notice that this, through a clever observation, can I not write this in the following fashion? What I am going to use is the sure complementation that we have seen just a couple of lectures back. Sure complementation. And notice once I have done writing, you cannot really miss it. It will be that obvious. So, I am claiming that what I have written here, this is actually equivalent to this inequality, yeah, and this inequality is nothing but an LMI, alright. So, that is basically precisely the point that I am trying to make here, is that this by no means looks like an LMI, it is a quadratic in X, right, but now this one is basically affine in X, and why is this equivalent? Just apply the sure complement, yeah. So, this part minus this times this inverse times this, and you will exactly have what you had on top here, right. And when you write this as greater than 0, what I mean by the 0 here is of course the 0 matrix. So, testing for this is tantamount to testing for the positive definiteness of this, right. So, because this now depends affinely on X, therefore, this is also an LMI. Of course, you might wonder what is this affine business, and that and similar other questions will motivate us to look for the next topic that we are going to now delve into, which is basically some ideas about topology. Okay. So, we have seen vector spaces, some ideas we have seen from linear algebra. Now, we want, and also from matrix theory, and then we have ventured into LMIs, and now we want to use these LMIs to solve for some optimization problems throughout this robust control course. Very, very important, right. We want to ultimately solve some optimization problem. We want to be able to solve at least some convex optimization problems, and also to be able to discern whether a given optimization problem is convex or not. If it is not convex, then it is that much harder to solve, right. But in order to understand those aspects of optimization, we need to understand something about sets, right. So, typically in an optimization problem, you are asked to get the best possible solution within some set, and if that set is convex, and if your cost function or your objective function is also convex, then we say it is a convex optimization problem, right. So, now in order to understand these ideas of convexity and other things like that, we need to get into a bit of topology, not very great details, but at least we need to be able to appreciate certain topological notions. So, that is exactly what we are now going to do. We will come back. This is hardly enough of discussions on LMIs, given that this is a course on robust control. LMIs will form the lifeblood of this course, right. So, this is far from being a sufficient discussion on LMIs. We will visit this very shortly, we will revisit this, okay. But before getting into that, since we have already introduced a term like affine, so far we have talked about linear independence, there is also the idea of so called affine independence, yeah, or affinely dependent or affinely independent set of vectors, right. So, in order to understand these notions, a bit of discussion, or maybe what might appear at this point like a digression into the ideas of convexity and some topological notions is warranted, okay. So, this discussion is to be continued, okay. Just to make a mental note, this is to be continued. We are not leaving this for the time being, we are just taking a small digression, that is all, okay. We will come back to this. Nonetheless, let me draw a line below this and say that now we are going to talk about some topological notions, okay. We already have a lot of the objects in place to delve into this discussion on topological notions. We already know what a vector space is, we already have ideas about norms of vectors. So, we have an idea about the distance, okay, distance between two points in a vector space, right. We have that idea, we have the idea of inner products, which when taken on of a vector with itself gives us the length of the vector, right. So, since we have already got certain ideas, we will not really go about very formally defining those, but loosely speaking we will assume that you understand what those ideas are, and then we will venture into this. So, the first important concept that we shall try to understand is one of neighborhood. So, the spelling can differ, either you use a OU or you just say OR depending on the British or the American spelling. Nonetheless, the idea is, what is a neighborhood? So, suppose again I am going to do this very loosely, quite slowly and in a rather informal offhand fashion. So, we have a vector space V, yeah. So, notice that when I am defining a new concept, I should not use any idea that I have already not introduced. So, when I am defining neighborhood, I am using ideas like vector spaces, which we are all very familiar with by now. So, we have a vector space, and suppose we have a basis for this vector space. Let us say that basis is V1, V2, Vn. So, naturally then this is a finite dimensional vector space, right. It is an FDVS, finite dimensional vector space, if you like. So, first thing we define is a unit ball, in this vector space, okay. So, notice that you cannot define this unit ball without defining this basis, and therefore, I might choose one basis, you might choose another basis. So, this way we describe this unit ball in a vector space will totally depend on our choice of basis, right. So, this is somewhat arbitrary insofar as the choice of basis can vary among the two of us, right. So, how do we define this unit ball? Here is how we define this B unit ball subject to my choice of basis Vn is defined as like so. You have alpha 1 u1 plus alpha 2 u2 plus dot 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 till alpha n un belonging to the vector space V. So, what is this? In the first place, every object in this unit ball is a linear combination of the objects of the basis. So, that means it is naturally an element that belongs to this vector space, but apart from that we constrain it. So far we have not constrained anything. So far, if you just cast your attention on what we have used so far, in this part of the definition it is nothing special. Anything that satisfies this property will definitely belong to this vector space V. So, this is nothing new here. Now, at this point is where we are imposing some constraint on, some additional constraint on this, where of course the alpha i's are real numbers. Again, nothing fancy about this. This is over the field of real numbers. But now, very importantly, we have this constraint that the summation of alpha I squared, I going from 1 through n, is less than unity. What does this mean? Notice, forget about any idea of orthonormality for the time being, okay. Yeah. So, if it is an orthonormal basis, you can imagine that this alpha I squared summation is like a sphere. You can think of some orthonormal basis, like in R3 you have x, y and z, the three orthogonal axes, right. Yeah. But remember, a basis need not be orthogonal set of vectors or an orthonormal set of vectors, right, even. I have not constrained anything, right. So, I can choose any bunch of linearly independent set of vectors, yeah, and that will suffice, that will satisfy the conditions of being a basis so long as it is a linearly independent spanning set. And then if we say that all we are constraining is to say that the square, sum of the squares of the coefficients is less than unity, it need not necessarily in your Euclidean space, for instance, it need not look like, it need not look like a sphere, it could look like an ellipse or an ellipsoid, right. That's all that's being said here. It's only when you have this orthogonality that you have this beautiful undeformed spherical or circular shape, depending on 3D or 2D or whatever, that too in the Euclidean space. So, while when we are talking about the topological space, the idea is very abstract, you would always do well to cast your attention back to spaces that you are very familiar with and can easily visualize. Of course, that does not always work. Sometimes these abstract spaces are beyond our grasp, and then we have only these abstract tools to deal with them. But in this case, so far as this is concerned, it does help to keep in mind that nowhere in the choice of this basis have we assumed orthonormality. So, this ball, although we have a tendency to think of a ball as something round or spherical, rotund, in this case it need not be so. It totally depends on what sort of a choice of basis you have made, alright. Okay. And in fact, they are also not normal vectors, right. So, these are not unit norm vectors. So, naturally, if I choose this basis, you are very free to choose, as a matter of fact, a basis B. Okay, this is not the symbol for basis, I am sorry. So, you are very free to choose the following as a basis, no, T1 V1, T2 V2 dot 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 till Tn Vn. Remember, you can always choose this where Ti's are not equal to 0. So, this is also equally legitimate a basis, right. And in terms of this new basis, you can define your, you can call this like V1 tilde, this is V2 tilde, and this is Vn tilde. So, in terms of this basis, you can define your ball, right, in terms of V1 tilde, V2 tilde. So, I mean, very loosely speaking, not just the shape, but even the size of the unit ball or the size of the ball, right, the open ball need not be the same. So, what is a unit open ball for me may not be a unit open ball for you, depending on your choice of basis. So, this unit ball, this idea of this being unity, is pretty loose in that sense. You can play fast and loose with this, right, because I have never restricted these to be either orthogonal or even normal vectors, each of them, right. Very, very important notion, right. Okay. So, this is a basis independent set, okay, sorry, a basis dependent set, I am sorry. So, this unit ball, this set that I have defined here, this is a basis dependent set, depends on the choice of basis that you make, okay. So, now having come this far describing what a unit ball is, now we are in a position to describe what a neighborhood is going to be. Okay, and that is probably what we will have time for in today's lecture, with the basic definition of what a neighborhood is. Okay, we will of course delve further into these topics in subsequent lectures. Okay, so now we are going to give some sort of a definition. Again, I do not want to scare you by giving this a very formal sort of a look. So, let me adopt the same semi-formal or informal sort of an approach for describing all of this. Suppose you have we have a subset, suppose we have a subset n of 0 which is contained in the vector space V. This is a subset, remember, not a subspace, it is a subset only. We call this subset to be a neighborhood of 0. Remember, a vector space must contain 0, right, the 0 subspace, that is the smallest subspace, the trivial subspace that you have in any vector space. So, we call this to be a neighborhood of 0 if there exists some basis. So, all this discussion we had about this being this open ball being dependent on the basis. Yeah. So now that is why it makes sense. So if there exists some basis, I am not saying there exists the basis, okay, or any particular basis. If there exists some basis, say V1, V2 dot 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 till Vn, such that the unit ball defined in terms of that particular basis, yeah, I am not writing this, I am just saying it out in loudly in words. So if I can find a basis such that in terms of that basis, when I cook up a unit ball, yeah, then that ball, yeah, is completely contained in the neighborhoods, in this set or the subset which I am checking for a neighborhood of 0. So if we can cook up some basis, remember, so very intuitively speaking you can think of this like, look, finding a big open ball is not really the problem, right. Whether something can be called a neighborhood, so I have a very small set. Now whether I can fit in a smaller unit ball within that small set, right, that is basically the challenge, yeah. So if I give you a large set, a big set, you know, as in contains a lot of objects around the origin, a huge zone, a huge area. Think of the Euclidean space when I am talking about all this, by the way. I mean, you know, it is very difficult to immediately take the jump from the Euclidean space to the abstract topological spaces. So just have the idea of Euclidean space in mind when I am saying this. So if you choose a huge region around the origin, yeah, with no punctures and everything in it, right, a solid region around the origin in 3D, and then it is really not a challenge to find this ball, this open ball, this unit open ball that is contained in this neighborhood. It is only when you choose smaller and smaller region, when you have chosen a small neighborhood around this origin, a small subset around this origin, yeah, can you still find a small enough unit ball subject to some choice of basis so as to fit it in. Essentially what I am saying is, look, you choose any V1, V2, V3, Vn, keep scaling it down by some common factor, say t, like here we have scaled each of them by different factors, you see t1, t2, tn, let us say you scale them all by the same factor t. So then each vectors, each element in the basis set, its norm gets reduced. So t v1, if t is very small, then the norm of v1 is much larger than the norm of t v1. Similarly, the norm of t v2 is much smaller than the norm of v2, right. So if you can play around with this parameter t and make this norm of each individual component in the basis smaller and smaller, then naturally this ball also keeps shrinking and getting smaller and smaller, and if this ball keeps getting smaller, then you have found a very small ball to fit in within that neighborhood. If you can find that ball to fit in within that neighborhood, then you can legitimately, actually I should not be using the term neighborhood, if you can fit it within that subset, then that subset qualifies as a neighborhood of the origin, okay. So in the next class we shall see that once we have this neighborhood of the origin defined or neighborhood of the 0 defined, then we can also arbitrarily define the neighborhood around any point in the vector space by a simple translation. We will give a somewhat formal description and then we will launch into subsequent topics, yeah. At the end of it we want to again come back to this idea of LMIs, yeah, armed with all the tools and ammunitions that we need from these topological concepts such as convexity, separation between subsets, etc., and then we will finally see the complete picture. So that is probably the content, going to be the content for the next lecture. Till then, take care. Thank you.